All right, guys, Mr. Antonucci here, and we're back with the second part here. We're going to look at part two of the fundamental theorem of calculus. So in part one, that established a relationship between the derivative and the definite integral. And now in part two, the fundamental theorem is going to provide us with a method for finding a definite integral without even using a Riemann sum. So it turns out that if f is a function that is continuous on the closed interval a to b, if capital F is any antiderivative of little f on that interval, then the definite integral from a to b of little f of x dx is equal to capital F of b minus capital F of a. What that's basically saying in notation is that to evaluate a definite integral, you take the antiderivative, plug in the upper and lower limits, and subtract. Okay, so let's run through some examples to show you how this actually is going to play out. So, um, part A, we have the definite integral from -1 to 2 of x squared. So, the little f in this case is x squared. It's continuous on the interval -2 to 1. So, the antiderivative, capital F, is the new exponent, or add 1 to the exponent multiplied by the reciprocal. And you don't have to write the plus c, and I'll show you why. Had we written the plus c, and then we do capital F of 1 minus capital F of -2, capital F of 1 would be 1/3 times 1 cubed plus c minus 1/3 times -2 cubed plus c. Oops, that should be a c. Okay, but this is being subtracted. Okay. Now notice the c's are going to cancel. And this is always going to be the case in this type of situation. So you don't have to write the plus c here when you're evaluating a definite integral. So you'd have 1/3 minus -8/3, which is 9/3, which gives us 3 in that case. All right, and the next example, we're going to go through it kind of a little bit faster. Okay, so for part B here, we're going to take the antiderivative of cosine. Since cosine is a continuous function, specifically on the interval from 0 to pi over 6, the antiderivative is sine x. That would be our capital F, and we're going to evaluate it from 0 to pi. Okay, so this bracket here just means evaluate at pi and 0 and subtract. So you always evaluate at the upper limit and then the lower limit, and then you subtract those. Okay. This is pi over 6. I forgot the over 6. I thought that was looking a little fishy. Okay, so sine of pi over 6 is 1/2, and sine of 0 is 0, so we get 1/2. For part C, the antiderivative of 1 over x is natural log of the absolute value of x. Now, with this one, we have to be careful because 1 over x does have a discontinuity at x equals 0, but the interval from the upper and lower limits from 1 to 2 does not include that value, so this function again is continuous on that interval. Okay, so we can keep going here by evaluating this at 1 and 2. Okay, so you have natural log of the absolute value of 2 minus natural log of the absolute value of 1, which would just be natural log 2, because natural log of 1 is 0, and the absolute values are no longer necessary. For part D, we have 1 over the square root of 1 minus x squared. This function is going to be continuous from basically -1 to 1, which includes the interval 0 to √3 over 2. So the antiderivative of 1 over the square root of 1 minus x squared is sine inverse of x. And then we're going to evaluate that at 0 and √3 over 2. So it's going to be sine inverse of √3 over 2 minus sine inverse of 0. which gives us pi over 3 minus 0, which is pi over 3. Okay, so another situation here that comes up is finding the area under the graph. So in this case, the problem is asking us to do it for e to the x from -1 to 1. So I have a picture of the graph here, and I'm just going to sketch the area. So it goes from -1 to 1, and the area is this region right here. All right. So if I superimpose a larger rectangle over this whole region, it goes from -1 to 1, so it's 2 units wide, and it's about 3 units high. So this has an area of about 6. Okay. But that's way bigger than the region we have. So we know our answer should be positive, and it's probably going to be around 3 because that's around half of that rectangle right there. Okay, so if we're asked to set up the definite integral that represents the area of this region, we would say that A equals the definite integral from -1 to 1 of e to the x dx. Okay, this function's continuous on that interval, so we could get the antiderivative, which is itself in this case, and then go from -1 to 1. So it would be e to the 1 minus e to the -1, which is e minus 1 over e. Okay, now that is the exact answer. If you were asked for the approximate answer, you'd plug that into a calculator and report the decimal to at least 3 decimal places of accuracy. All right, guys. Well, that's it for this one. Hope that was helpful to you. And as always, reach out if you have some questions. Take care.